Today we will learn the science of shotcrete, history and modern techniques and machinery. Shotcrete has a rich history, evolving from early 20th century experiments to today's advanced robotic systems. Modern techniques.
Welcome to this explainer. Have you ever stood inside a massive underground transit station, or maybe looked at one of those totally custom freeform swimming pools, and just wondered how on earth it was built? Traditional concrete requires a ton of rigid formwork to hold it in place while it cures. But today, we're exploring a highly engineered process that literally throws all those wooden and steel molds right out the window. We are diving into the absolutely fascinating science of shotcrete.
Here is our roadmap for today. We're going to cover what is shotcrete, the chemical recipe, dry versus wet mixes, machinery and spraying methodology, the power of reinforcement, and finally, tunneling and modern uses. Let's just jump right in. So think about the fundamental challenge of modern construction for a second. If you need to build a curved tunnel crown deep underground, how do you get wet, incredibly heavy cement to stick to the ceiling without gravity just immediately pulling it down and ruining the entire structure? Well, the answer isn't pouring it. It's shooting it. The secret is actually right there in the definition itself. Shotcrete is concrete or mortar conveyed through a hose and pneumatically projected at high velocity onto a surface. That high-velocity impact is absolutely crucial here. The sheer force of the ejection from the nozzle actually compacts and consolidates the concrete at the exact same time it's placed. There's no leveling, no vibrating it in a mold. It just adheres instantly.
And this timeline brilliantly illustrates just how far this tech has come. Back in 1907, an American taxidermist named Carl Akeley invented this cement gun. Now, there's a common historical myth floating around that he used this to build animal models. Actually, scratch that. The truth is he invented it specifically to repair the crumbling facade of the Field Columbian Museum in Chicago. Fast forward to the 1950s, the modern wet mix process was devised. And then by the 1970s, engineers introduced steel fiber reinforced shotcrete, which transformed a simple museum repair tool into a literal cornerstone of heavy civil engineering.
Moving on to Section 2, the shotcrete recipe. Mixing for maximum adhesion.
It's honestly just like baking. If your ingredients are off, the whole thing falls flat, literally right off the wall. Here's a typical mix designed for a really high compressive strength of 48 megapascals. You've got your standard cement, water, and sand. But look closely at the coarse aggregate. It is strictly limited to a maximum size of 10 millimeters, which is often called gradation number 2. And this is a very strategic choice. Larger rocks ruin the pumpability, and frankly, they just bounce right off the wall. It creates this wasteful problem known as rebound. So keeping those aggregates small ensures proper compaction.
Now, the really crucial point here is how you fight gravity. Notice that 40 kilograms of silica fume in the recipe. Silica fume makes the mixture incredibly dense and, well, sticky, which is absolutely essential for overhead applications so it bonds directly to the rock or substrate. Engineers also use Type 3 high early strength cement and chemical set accelerators that get injected right at the nozzle. This forces the wet concrete to stiffen almost instantly the second it impacts the surface.
That brings us to Section 3, dry versus wet mix, the concrete showdown.
Think of this like a culinary question. Do you want to mix your pancake batter in a bowl before you cook, or mix the dry powder and water directly in the hot pan? In the dry mix process, which was originally trademarked as gunite, dry ingredients are blown right through the hose, and the operator manually adds water at the nozzle. It offers amazing flexibility for remote sites, but it's prone to a lot more dust and rebound. The wet mix process, on the other hand, premixes everything, like batter in a bowl, before pumping. This guarantees highly consistent quality, which makes it ideal for massive, large-volume applications like tunnels where you really can't risk any delays.
Section 4, machinery and spraying methodology, from pump to wall.
Okay, so having the perfect mix doesn't mean a thing if you don't apply it correctly, right? The methodology involves 4 strict steps. First is meticulous surface preparation. You have to remove any loose dust or rock that could break the bond. After mixing, we hit step 3, the application. And the absolute golden rule here is to apply the shotcrete in incremental, thin passes known as lifts. If you try to spray a thick, heavy layer all at once on a ceiling, the sheer early-age weight of the wet concrete will just pull it straight down. So you spray a thin lift, let those accelerators stiffen it up, and then apply the next one.
Now, in modern infrastructure, doing this by hand is often way too dangerous or inefficient. That's why remote-controlled robotic shotcrete arms are widely used in deep mines and tunnels. These robots are incredible. They're sometimes integrated with LiDAR technology to provide real-time profiling. This ensures the shotcrete is applied at the exact uniform thickness required. It totally eliminates overspraying, which, if you think about it, just adds unnecessary dead weight to a delicate tunnel roof.
Moving to Section 5, the power of reinforcement, the structural secret sauce. Concrete is fantastic at handling compressive, squeezing forces, but it's really brittle under tension. To hold a massive tunnel open, it needs reinforcement. Historically, workers would literally pin heavy steel wire mesh to the rock wall before spraying. But traditional wire mesh has some pretty critical flaws. It's incredibly labor-intensive to install on jagged rock, and more importantly, when you spray concrete over a grid of steel wires, the concrete tends to bounce off those wires, leaving empty air pockets behind them. This is a highly dangerous phenomenon known as shadowing, and it creates voids that severely weaken the bond between the shotcrete and the rock.
To solve this, the industry shifted to the real hero of our story: steel fiber reinforced shotcrete, or SFRS. Instead of hanging a steel net on the wall, thousands of small, discrete steel fibers are mixed directly into the wet concrete matrix itself. When sprayed, these tiny fibers provide multi-directional reinforcement throughout the entire thickness of the material, completely eliminating those dangerous shadowing voids caused by wire mesh.
And the magic number for these fibers is an aspect ratio of 40:65. That is basically the length of the fiber divided by its diameter. Engineers use specially designed hook-end steel fibers that fall perfectly into this ratio. This specific geometry maximizes the anchorage of the fiber within the concrete. It essentially transforms a brittle, easily crackable material into a highly ductile, tough composite that can bend and stretch under immense loads.
And finally, Section 6, Tunneling and Modern Uses. Masterpieces of engineering.
Let's bring all this science together in some real-world masterpiece projects. I want you to imagine the extreme engineering challenge of digging a tunnel through weak, thinly sliced rock, what geologists call 1 centimeter foliated rock. As you dig, gravity instantly tries to pull those thin rock layers down, in a structural failure known as slabbing. If you applied a thick, heavy layer of traditional concrete here, it would just act as a dead weight and pull the fragile rock down even faster. Shotcrete is literally the only solution.
By spraying thin lifts of high-dosage steel fiber-reinforced shotcrete, engineers create a flexible lining. The goal isn't just to hold the weight up. As this quote perfectly summarizes, the toughness of the system allows the lining to act as a deformation-driven support, absorbing geological energy without brittle failure. The steel fibers stretch and bridge the tiny planes of weakness in the rock, physically absorbing the shifting energy of the earth itself. It's wild to think about.
But hey, it's not just for deep underground mines. The exact same principles of maximum adhesion and moldless application are used all around us every day. It's how those custom freeform swimming pools are carved into backyards. It's used to rapidly rehabilitate aging bridge decks without having to completely dismantle them. You'll see it stabilizing steep slopes next to highways, securing deep excavations for skyscraper parking garages, and even forming the perfectly smooth, curved bowls of local skate parks. The versatility here is just incredible.
Which leaves us with this final, somewhat provocative thought. As robotic automation combined with LiDAR mapping continues to perfect this spraying process, and as engineers develop brand new, eco-friendly, low-carbon geopolymer mixes, we really have to ask, is the era of building expensive, wasteful wooden molds coming to an end? Will shotcrete soon render traditional poured concrete entirely obsolete? It is a fascinating future to keep an eye on for sure. Thanks so much for joining me on this explainer, and keep questioning how the world around you is built. See you next time.
Subscribe to Core Concept for more insightful content. Learn, understand, apply, and grow with us. It's a knowledge-sharing channel. Subscribe now.